All right, we're going to talk about applying the Laplace transform to systems of differential equations. So we've seen and we've worked with in the past in this unit Laplace transform of a differential equation. We know that when we apply the Laplace transform to an initial value problem, we end up with an algebraic equation that then we can solve for the transform, and then we apply the inverse transform to get the solution to our initial value problem. So today we're going to apply that to a system of differential equations. We're going to apply the Laplace transform to a system of differential equations, which will give us a system of equations in the transforms of our solutions. And then we apply the inverse transform to each of those to get the, we solve the system of equations using our usual methods. And then we apply the inverse transform to each solution to get the solution to our system of differential equations. Our book gives us several physical examples, coupled springs, double pendulums, electrical circuits. There are others that could result in a system of differential equations, initial value problems that we could apply the Laplace transform to. So I just want to go through a couple of examples. So our system here is dx dt plus 3x plus dy dt equals 1. That's our first equation. And then we have dx dt minus x plus dy dt minus y equals e to the t. And our initial conditions, x of 0 equals 0 and y of 0 equals 0. Previously, we would have written x prime, matrix x prime equals 3, 0, negative 1, 1, x plus 1 e to the t. That's how we would have written this equation in matrix notation, and then we would have found the eigenvalues and eigenvectors, etc., to solve this system. But today we're going to use the Laplace transform. So we're going to apply the Laplace transform to each equation. So when we do that, we get x of s minus x of 0. I'm going to write out all the pieces here, plus 3x of s plus sy of s minus y of 0 equals 1. And for the second equation, we get x of s minus x of 0 minus, we have the Laplace transform of x, so that's x of s, plus y of s minus y of 0 minus y of s equals, this should be the Laplace transform of 1 is 1 over s, and the Laplace transform of e to the t is 1 over s minus 1. So this is our system of equations that we need to solve for x of s and y of s. So I'm going to rearrange and gather terms, and I'm happy that x of 0 and y of 0 are 0, so we don't have those that we have to deal with. So I'm going to gather things together, and we get s plus 3 x of s plus s y of s equals 1 over s, and s minus 1 x of s plus s minus 1 y of s equals 1 over s minus 1. So this is our system of equations that we need to solve for x of s and y of s. So we can use any method that we want here. We can use substitution, we can use elimination. Our coefficients are this s plus 3, s minus 1, s minus 1. So we're going to do some algebra. And what I would recommend, and I'll talk about it here at the end of this lesson, I will talk about Kramer's rule for a 2x2 system. Kramer's rule lets us solve systems of equations using determinants. So I'll talk about that in just a second. We use some algebra, and after our algebra we get x of s equals 1 minus 2s over 3s over s minus 1 squared. And y of s equals 5s minus 1 over 3s times s minus 1 squared. So now we need to apply partial fractions to each of these. We apply partial fractions, and we get that x of s equals 1/3 1 over s minus 1/3 1 over s minus 1 minus 1/3 1 over s minus 1 squared. And I'm thinking of this as minus 1/3 1 over s, and we're evaluating that. S goes to s minus 1. So we have an exponential function here that's going to be multiplying our solution. And we get y of s equals minus 1/3 1 over s plus 1/3 1 over s minus 1 plus 4/3 1 over s minus 1 squared. And again, we can think of this as 4/3 times 1 over s, and we're evaluating that at s minus 1. So we apply the inverse transform to each of these, and we get x of t equals 1/3 minus 1/3 e to the t minus 1/3 t e to the t. And we get y of t equals negative 1/3 plus 1/3 e to the t plus 4/3 t e to the t. So, as we might suspect, we end up doing a little algebra. Laplace transforms often involve partial fractions. But it's a relatively straightforward method. Works very nicely for initial value problems. Now, one benefit for a first order system of differential equations, is it easier or less work than doing our matrix methods? Maybe, maybe not. But we can apply the Laplace transform to second order initial value problem systems, which we did not have a method for previously. So let's look at that. So d squared x dt squared plus dx dt plus dy dt equals 0. And d squared y dt squared plus dy dt minus 4 dx dt equals 0. These equal 0. That's nice. I'm going to say x of 0 equals 1, x prime of 0 equals 0, y of 0 equals negative 1, and y prime of 0 equals 5. Let me make that 5 a little, there we go, 5. So just like before, we're going to apply the Laplace transform to each equation. We get an algebraic equation that then we need to solve for our transforms, and we apply the inverse transform. So transform each equation. So we get s squared x of s minus s x of 0 minus x prime of 0 plus s y of s, sorry, x of s minus x of 0 plus s y of s minus y of 0 equals 0. Transform of the first equation. Second equation, s squared x of s, sorry, x squared y of s. I'm trying to rearrange things already. Y of s minus s y of 0 minus y prime of 0 plus s y of s minus y of 0 minus 4 s x of s minus x of 0 equals 0. So that is our system. I'm going to plug in the constants here and gather our terms. So we have x of 0 is -1, x prime of 0 is 0, y of 0 is -1, and y prime of 0 is 5. So we're going to substitute those in the appropriate places. And I'm going to also, what I was doing here before was I'm going to put the x of s terms first and the y of s terms second. So we have our system of equations arranged in a nice way. So we get s plus 1. I'm going to do one step between here because we need to, I'll do some simplification. So we get s squared plus 5 x of s plus s y of s equals the Laplace transform of I'm sorry, I'm putting the constants on the right hand side. So this would be my constant here is s, and that comes from here. And then I get s squared plus 5 sorry, s squared plus s y of s minus 4s x of s equals -5. And the -5 comes from this minus y prime of 0. And let me double check here. This is not an s squared plus 5. This is an s squared plus s. The s comes from s x of 0. So that's a 1. So I can divide this entire equation. And this, let me double check here. This is a minus s, not a minus 5. And that comes from, where's the s? sy of 0. So this gives me a minus s that I, minus -1. So this gives me minus s minus -s. So this gives me a positive s that I subtract from both sides, and I get a -s. There we go. So I can divide each of these equations by s. And then I'm going to put this x of s first and the y of s second in this equation. So got my constants plugged in here, got all my s's and 5's worked out, and we are good. So I'm going to rearrange here, divide everything by s, and I get s plus 1, x of s, plus y of s equals 1. And I get, for my second equation, minus 4 x of s plus s plus 1 y of s equals negative 1. So we do some algebra here. And we get x of s equals s plus 2 over s squared plus 2s plus 5. And we get y of s equals negative s plus 3 over s squared plus 2s plus 5. We need some partial fractions here. We're going to complete the square as well. So we get x of s equals s plus 1 over s plus 1 squared plus 4 plus 1/2 of 2 s plus 1 squared plus 4. And y of s equals s plus 1, negative s plus 1 over s plus 1 squared plus 4 plus 2 times 2 over s plus 1 squared plus 4. And I'm going to say this comes from, not from partial fraction, but from fixing up our constants so that we have the shift compatible in each one. So we have a shift of s plus 1 in each term. And we apply the inverse transform now. We get x of t equals e to the minus t cosine 2t plus 1/2 e to the minus t sine 2t, and y of t equals negative e to the minus t cosine 2t plus 2 e to the minus t sine 2t for our solution to the second order system of differential equations, which we did not have a method for previously. And I'm going to go back up here, make sure when you set up these systems, because our equation is not necessarily set up in a nice order. Once we get our system to use our matrix methods, our linear algebra methods to solve our system, we want our x of s as the first term and the y of s as the second term to keep everything straight. All right, and I want to talk really quickly about Cramer's rule. Cramer's rule is a method for solving systems of equations. It involves the determinant of the coefficient matrices. So we have a system of equations that we can write as a matrix equation. Ax equals b. A is an n by n coefficient matrix. X is a column matrix. With n elements. And B is also a column matrix with n elements. So our ith variable, x sub I, is the determinant of a sub I over the determinant of A. And what we mean by A sub I is matrix A with the ith column replaced by B. So let's go back to our first system that we had here, where we had, this was our system. So our coefficient matrix is S plus 3, S minus 1, S minus 1. And we have x, y, and that equals our constant matrix there was 1 over s and 1 over s minus 1. So what this tells us is that x equals the determinant of the matrix, this matrix, but we're replacing the first column by this matrix. So 1 over s minus 1, s minus 1, over the determinant of this matrix, s plus 3, oops, s minus 1, s minus 1. So we get, for the determinant here, we get 1 over s times s minus 1 minus s times 1 over s minus 1 over the determinant here is s plus 3 times s minus 1 minus s times s minus 1. And then we simplify this, and you'll see if you simplify this, you end up with what we wrote here for x of s. And notice the denominator is the same for both x of s and y of s. Well, that's the determinant of the matrix A. If I go back here, that's this determinant. And if I wrote y is going to be the determinant of the matrix s plus 3, 1 over s, s minus 1, 1 over s minus 1. So I'm replacing the second column with this column, and we divide that by the determinant of matrix A. Find that determinant, simplify it, and we end up with what we got here for y of s. So I think Cramer's rule for a 2 by 2 matrix especially is the simplest way, I think, to solve that system of equations when your coefficients are things like s plus 3 and s and 1 over s minus 1, etc. All right. I think this homework is incorrect, so give me just a second and I'll write it up here. All right, now I have the correct homework. Page 336. Number 1 through 11.